Okay, so my pleasure to give the last summary talk. Okay, it doesn't move. What happened? Stand.
What's that?
Something wrong with my computer? Sorry. I don't know what happened.
Oh.
Okay, good. So that's that. So I will talk about holographic QCD model in this part. I think Prem, yeah, of course he already left, but I think he talked about some basis of string theory. So I will give you a little bit. Well, because I don't know so much about the string theories, frankly speaking, because I'm from QCD background. But I give a brief history of this QCD and the string theory. As I said that actually string theory, of course you know that, string theory was born out of attempts to understand the strong interaction at the end of 1960s and also at the early of 1970s. So actually, because of that, at that time, many meson states and hadrons were observed in the laboratory. So people want to understand something about the strong interaction, and they found that. The string picture actually can describe this rich trajectory of the hadron spectrum. Oh, sorry, microphone. Okay. So yeah, I checked actually this is a spin, not the radio direction. But anyway, both these rigid trajectories, also holds for spin. For spin and also for this radio excitations. But here this J is spin. Okay, so anyway, with this string model, this string picture can give you this rich trajectory of, so basically this mass square is proportional to the some quantum number here. And why it's so something happened to my computer or what? Sorry for that. But what happened, I don't know. Shall I please? Yeah, but it doesn't work. Huh? 右上角。Oh. Oh, sorry. Okay. So actually, the string model is is related to this confinement because this gives you this linear potential between the two quarks, the quark and the anti-quark. So and this also kind of how to say? So this is this string picture, of course, can be. So some people proposed that this string is kind of a Kanner flux tube of QCD. So while the comparing with this have two superconductor, so they thought that okay, so there is a kind of duality here. Well, it's kind of dual. So here this is so basically in the vacuum you have some magnetic monopole condensation, and this would squeeze the kind of electric flux. So basically this kind of electric flux will bind this quark antiquark. So this is this string is related to this confinement. And okay. So in 1970s, of course, some work related to this QCD and the string theory that I think taught in 1970s. He found some kind of duality between effective theory and the string theory. So basically, this is in the NTU-CTP limit. So you can find that. Okay, I think Prem, he talked this NTU-CTP expansion yesterday. So I may be just go through that. So basically, what Toft found that at no energy, QCD at no energies, actually he found this kind of when in the natural coupling, when the coupling is notch, he found some kind of dual weakly coupled kind of duality between weakly coupled string theory with strong coupled QCD. Well, so this is kind of you can read this kind of dual from this vacuum to vacuum amplitude from in NTU-CTP gauge theory, and this vacuum to vacuum amplitude in string theory, and you see this structure is quite similar, and then you can read that okay, this so this super Yamir this is the string tension. Okay, this is the string tension. Yeah, GS is string coupling, and which one? Yeah, this one is inverse string tension, and then basically you can read this dual from these two series. So this basically suggests that closed strings would be blue balls and open strings would be mesons. I think this is a picture at that time. But however, string theory, strings was there were some problems, of course, to make a string theory become the true theory of QCD of strong interaction. So because this strings has a kind of always include a graviton. So basically this string theory is now a kind of normally regarded as a model for quantum gravity, not for QCD theory, not for strong interaction. And of course, after 1970s, because the success of QCD, so basically people regarded that QCD is a fundamental theory for strong interaction. Even though, of course, in this theory, the perturbative QCD is basically conformed, is basically checked very carefully by deep inelastic scattering experiments. But in the non-perturbative QCD regime, challenging still remains there. Of course, string theory developed kind of to make itself a theory of everything. But from 1997, so Metatena made such kind of conjecture that the string theory on ADS5 is due to a super Yang-Mills theory. So this gives some hope that okay, maybe it's hopeful that one can find for any gauge theory, so one can find the dual of the string theory or the gravity dual of gravity. So this is of course very exciting in some sense. But as we know that QCD, of course, is not conformal. So basically, so here now we don't know what's the dual string theory of QCD, right? So because we know QCD is non-conformal. So whether we can find, whether it's possible to find a string theory dual to QCD, this is actually many people now are working on this, both from top down and also from bottom up. So today I will so actually in this talk I will basically try to construct a 5-dimensional quadratic QCD model, and it's a kind of a bottom-up picture. And I hope that I can build some connection between the QCD dynamics and the geometry. But of course, I mean, from top down, there are also lots of efforts there. So, but anyway, I'm not expert from this part. So I would not touch this part. I'm not able to do that. Okay, but in this framework, I would say that there are many efforts. So I will show you that some efforts to try some kind of naive try, and also some because ADS5 is not cannot really describe QCD. So some people have some intelligent guess to guess the deformed ADS5 metric. But at the end, I will give you a kind of systematic framework, which actually my student here, Dan he worked a lot, and I think we made some progress. I like this because this framework kind of resembles the RG flow in some sense. So I will basically slowly go through from this to this. So at the end, I will talk about our work. Okay. So okay. So I will basically introduce you briefly some kind of hologram QCD model for hadron spectrum. This is actually very very rough. So people just try by using ADS5 metric because and say how good it is to describe the hadron spectrum. So this is done by in 2005 by these groups, and actually it worked quite good, not very bad. So they just took the ADS5 metric, and of course they introduced a kind of hard cutoff. But for the hadron in action, actually they introduced these Meson degrees of freedom. This is like a 5-dimension linear signal model in some sense. Okay. So basically, I mean, this looks like, so basically the flavor symmetry remains there, right? And of course, you need to introduce the dual between the operators and the fields. So this is, but for the dimensions, you have to, I mean, for this 5-dimension mass, you have to get it from this ADS-CTP dictionary. So this is the only way. This is the only place the ADS-CTP place here. And with this, then you can solve the equation of motion, and then you can produce the hadron spectra. And they calculated this the ground state, the lowest ground states. So basically, pion, rho, and a vector. Okay, So pseudoscalar vector, actual vector, and also decay constants. And they found that, okay, this comparing with experimental data, actually this results in this simple model is actually not bad. You see, it's around 80 to 90% agreement with experimental data. So it's fine, right?
So can I ask a question? Can I ask a question? What is the boundary condition they impose on the IR cutoff?
Sorry?
What boundary condition they impose on the IR cutoff? You say this is 85, but they put the IR cutoff.
Yeah, they have.
What boundary condition they impose?
Well, okay, they introduced, how to say, for this scanner, they have kind of, this scanner field. They introduced, how to say, it's kind of, they introduced kind of chiral condensates here for this X. They,
No, and for the scalar field in the bulk, do they impose directly boundary condition or Neumann boundary condition or something else? Do they impose? They supposed to solve the equation motion. In the bulk,
equation motion. Yes.
What boundary conditions they impose at the IR?
At the IR.
Yeah. For the
They
scalar
took,
field they impose.
yeah, they took okay. For this scalar field, they took well, they have some kind of current mass and okay. So this okay, I can maybe write it there. But you can check this with the paper, right? But actually, this so this. I think at IR they fix this. You see, they have some parameter for this. And this sigma is actually chiral condensate map. So I think this is IR condition.
I mean, Z equal to Zn.
Z equal to, at IR, yeah. This is okay. This is okay.
Z equal to 0 is UV, right? Z is
Z equal to 0 is UV.
Right.
I mean, this is IR, right? This is IR, right?
Right, yeah. So at Z equal to Zn, they impose this as a boundary condition. Is that what you say?
Z equal to
Zn. So the bulk Z equal to
yeah. Z equal to 0, yeah. And okay. Oh, yeah. This might be UV, right? Oh, this is UV
Right,
boundary.
I think so.
Okay, sorry.
My question is that the IR, what is the boundary? We don't know.
IR, do they have okay. I think this is all they need for the okay.
It's okay.
Yeah, I think this is I think this are the parameters. This is for okay at IR and yeah. I think this is for UV. Yeah, this is the parameters they need. Okay, but you can check very carefully also. Okay, and yeah, so it's not that bad with this simple model. But however, in this model, for higher excitations, in this hardware model, there is no ridge behavior because the mass square grows as n squared. So this is so. In order to improve this, they introduce a software, and this software is described by this dilaton field here. This is a kind of quadratic dilaton field. And but still they use this ADS5 metric. So with this, they can, at least for row meson, in this model, they can produce this ridging behavior with this dilaton field. And Of course, I mean, this, even though for room meson this works, but this does not work for all the mesons. For example, even though for room meson there is kind of range behavior, but for actions, for actual mesons, this does not work not work well. I will come back to this later. But this, I mentioned that this work was together with Yang Yi and also my previous PhD student.
So how about the tensor meson?
Tensor we are working on now, but Kat, Andreas Kat. Actually, at the end of July, he told me that tensor mesons was very bad in this model, within hardware model and this social model. It was bad, but we are now, because he suggested us to do that, so we are now doing that in our own model. I will talk about it later.
So for axial mesons, experimentally, is there a sort of follow the ratio?
Yeah. I will come back to that. Yeah. But this is just to show you. Well, I mean, for naive trying, so something worked, but something doesn't work. And another part is for the confinement. So basically, the confinement is described by this linear quark potential. So you will see that how this how you can derive this from this holographic QCD framework. So this is for QCD we have this kind of Conner potential. So of course we have a Coulomb part and also this linear part plus constant. Yeah, okay. I will not mention this here. So to calculate this heavy quark potential, you need to calculate this Wilson loop, and you can extract this heavy quark potential from this Wilson loop, right? So you need to calculate this Wilson loop. So how they do this in ATSFT? So this was done by Manazena and also some Korean people. And of course, this is a kind of holographic dictionary. So basically, you have to calculate this Wilson loop, but you have embed this in your fifth dimension, right? And so this NG action will give you this heavy quark potential. So, but for ADS5, if you have an ADS5, so this will only give you a Coulomb potential. So basically, only this this part. Only, I mean, for if you have ADS5, then you can only get this part. You will never get this linear part. So basically, you need to do something, right? You need to put something to get your linear potential. And there are kind of some efforts to improve this. For example, this Andreev-Zakharov, and they introduced a metric, because you need to modify this metric. And they introduced such kind of, also, it's a little bit like this dilaton field, but not in the action, but in the metric. So basically, this is, if you look at this, is just ADS5. But so basically, this is a kind of deformed warp factor, right? So basically, they introduce this kind of deformation here, and then in this framework, they can produce this linear potential. So basically, you have to do something. I mean, to deform your warp factor, your ADS5. And of course, many other people also tried. For example, in this white paper, and he tried many kind of deformation. And then they found that actually this Andreev-Zakharov, this simple quadratic term deformation is actually works better than others. So even though this they have for other deformations they introduced more parameters, this one, the simplest one, works better. Okay, and also some other people from Heidelberg, they introduced some kind of intelligent gas, how to deform this ADS5 metric. So, okay, the idea is that, okay, ADS5, because if you have ADS5, it's a conformal theory, right? But you know that the QCD theory, the coupling is running. Because for conformal theory, the coupling is a constant, it doesn't run anyway. So basically, okay, they said, okay, how about they just deform this warp factor and then to resemble such kind of running coupling behavior. So basically, this is QCD running coupling constant. So they just replace this P as 1 over Z. Z is the fifth dimension, and then they found such kind of deformation. Well, I mean it's a little bit different from this, but almost the same. And then with this, they can also produce. Oh, sorry. But anyway, they can produce this linear potential. And we also, well, it's kind of just naive try, of course. We also introduced some kind of deformation, and we also can produce this linear potential. So it's actually not bad, because you see that this is counter potential, and we can produce this quite good. But okay, but until now, I mean, it's kind of still. I mean, you can try. I mean, it's a kind of we try, and I mean, we don't really understand what's there. But in this framework, actually we well, at the moment, of course, this metric is kind of put by hand. But we solve this kind of self-consistently by using this Graviton-dilaton system. So in this framework, so basically, it's like this. So this is a kind of Graviton-dilaton coupling system. So what we did is actually we input this kind of deformation, and then of course, because this is actually related to this kind of dilaton field, right? So of course for conformal theory, so this dilaton field, this potential is like this, and I mean, you need to self-consistently solve this Graviton-dilaton coupling system. And I mean, actually there are 3 different ways to do that. So, so for example, maybe somebody here knows that, for example, GKN group, they input, and also Gapser. So they input this dilaton potential. And of course, this dilaton potential in some sense can resemble the beta function. And then they can solve this metric